random clock talks with a little more observation of some lathe operation. This is the same lathe as we ended clock talks number 2 with, and let's look at the tool slide. The 3-deck tool slide, and a crossbar underneath that gives us the alignment so that we can remove and reinstall on the lathe and keep things in dimensional order, and the tool post with an adjustable height tool holder. We actually rotate an eccentric washer that is underneath the tool bit to set the height of the bit. So let's set this about here. We use a little pin handle to tighten the tool bit, and we'll see how that we can progress across here. Let's touch the focus a little, see if we can improve it a little. Looks like we can't. And I have to find my eye loop. So let me cut the camera a moment. Back on the camera, and I have my eye loop. I see pretty well without the eye loop, but I dare not get a chip in the eye. So let's see what we have here. Let's start the motor and look at this situation. We'll back the tool slide out and go in and take a little bite on the, you can see the chips flying, and here the motor's not laboring, and you can see the type of thing that a watchmaker's lathe can do. Now, if we're doing something of serious consequences and working to a dimension, we have to do something more than just watch the chips fly and say that it looks pretty. These, the barrel here on the longitudinal feed, the barrel on the cross feed, these have calibration markers in them, but they are pretty rough. They're really not, they're a good indication of what you're doing, but they're far from being perfect. So let's pick up a couple of tools that we can use and see what we can do for finer machine work. So we'll cut the camera a moment while I pick up the tools. All right, let's progress a little further. Here is, find a place in the camera, is a 1-inch dial gauge, which gets mounted over in the rear of the horizontal slide. I think that what I'll have to do is to back the camera out so that we can see the dial gauge, and the second dial gauge mounts right over here for the this is for the longitudinal slide. The one I call the longitudinal slide is really the horizontal slide. So let me see if I can get the camera backed off to where that we can see these two gauges. Camera's on again. Let's see what we can find here. The gauges are not too visible because of the lighting. We've got some problems. Here's the gauge for the horizontal feed. Here's the gauge for the longitudinal feed. You can probably see this particular gauge here. Now let's take, for instance, a cut and see what we have. Watch the tool bit. Watch in this area. Watch for the chips, and we'll make a cut. Chips are flying, and we go down some depth and back out. Now, let's take our caliper, measure the diameter of this particular turning here, and we slide that off, and I'm reading 471 thousandths of an inch, 0.471 inch. Now suppose that I would like to take that to 0.475. That is to I can't do that. I can't make it bigger. I'm making it smaller. So let's say that we want to take it to 0.460. That's a reduction of 11 thousandths of an inch in the diameter. All right. This gauge, the gauge that we have here, is measuring on the radius in the lathe. That says that we have to pull up half as many thousandths on the gauge as we want to reduce the diameter of this. So let's say that we pull up about 4 thousandths of an inch and see what we have. Now the technique here is to turn this to a 0 setting, then we'll crank in, and let's do this in a couple of steps. Here's 2 thousandths of an inch that I've dialed in, and let's take that off and look at it. Let's see what we got from that point. All right, we're at about 466. Let's pull up 2 more. And see what we have. The chips are very tiny at this point. They're flying fast, but they're very tiny. And let's make a measurement again. And we are at 462.462. Pull up 1 more thousandth of an inch and see what we can do in this final cut. The chips are hardly visible at this particular cut, and come back out, see what we have. It's difficult to tell what we have there. I am either 459 or 460. We measure this with the pressure on it there and pull off easily. Be sure that we don't stretch the jaws or open the jaws. Looks like that we're on 459 thousandths of an inch. Now, when we look at that, you see how easy it is with the watchmaker's lathe, a tool slide, and a good dial indicator, how easy it is to work to within plus or minus 1 thousandth of an inch. 1 thousandth of an inch. We can do the same situation over here on our cuts, on our longitudinal cuts, by reading the gauge here. It's really easier to hit a dimension on the longitudinal cut than it is the horizontal cut. If you give it a thought, you can see exactly why. 1 thousandth of an inch on the gauge is 1 thousandth of an inch on the cut, on longitudinal. On horizontal, on the cross feed, we're measuring radii rather than diameter. So that says that the gauge on the longitudinal cut has twice the sensitivity of scale as the same gauge would have in the horizontal cut. But what we find, it is no problem at all to work to within plus or minus 1 or 2 thousandths of an inch with the watchmaker's lathe with just reasonable set of tools. Now, let's slip this off and look at it again. I have to remove this gauge to pull the slide past the bed, or well, I have to remove it because there is a tang on the bottom of it. But this comes off like this. This gauge over here slips off there. The tool slide, you have all kinds of problems with dirt and trash on it. You use a little soft, about 1 inch wide paintbrush, and you clean all this up. So that's the technique. That's the technique that you have in using a 3-jaw chuck, using the slide rest. Now let's look at the slide rest, some features that that we can also do on this. Let's lock back up and take our tool key. Notice what happens when I flip the tool key in this right here. It's like that. I can rotate this upper slide. The upper slide can be rotated within certain limits. If I carry it on around, I must remove my dial gauge block here. Now, as I do that, this particular crank here, and I'm bumping down on the bed there. It says that we have to be within certain limits to do that. This would have to be out about like this for this to overhang the bed. Now I can turn at an angle. This tool is traveling at an angle, no longer parallel with the bed. This dial here carries me at this angle. So you see, we maintain a 90-degree relationship between the two axes here, but they are rotated with respect to the bed. You say, well, how do we get into the chuck if we pull this over the bed? Well, that's pretty simple. You just move the headstock over. We just slide the headstock over like this, and that solves that particular problem. That's why that we have deep grooves on the drive pulley, and we have a screw. I don't know if this can be seen, but it's straight down right here that we can release the motor and slack the belt slightly. As a matter of fact, I can tip the motor at an angle to accommodate that situation. So this is some of the features that you have in the lathe, and when it is set up for clock making. We turn this back. There is an index over here that allows us to return to 0 and lock the tool up again. Let's turn off the camera and we'll look into another facet of lathe. Let's look at another type of chuck that we can use on the watchmaker's lathe. This chuck that we've been using is a 3-jaw chuck made by Boley and Lennon in Germany. The best I can tell, other than the name that's stamped on it, it's comparable to the Boley that is sold in this country in every respect. These chucks are available. See if I can get back into the focal point of the camera. This hub and spindle that's on this chuck is detachable from the chuck body. What we find here, when you buy the chuck, you get the basic chuck, and then you buy the spindle to adapt to the particular lathe that you intend to use it on. This spindle right here is a Mosley No. 2 spindle. This lathe that I'm using is a Webster Whitcomb spindle. Now you've got a little problem in that situation, because the tang length of this part of the chuck is wrong. As a matter of fact, the Mosley No. 2 tang is longer than the Webster Whitcomb tang. And what you have, and I have several drawbars with different shoulder lengths, and I have several spacers to go on these drawbars that I can make up that type of correction with. Let's look at this chuck. This is also made by Boley and Lennon. It also has the Mosley No. 2 tang on it, and I screw up here, and I'm not tight. I've got to have the spacer under the drawbar to pull this up. There we go. Pull the index key out. Let's look at this. What do we have here? Let's try adjusting the focus again. I have a problem on the focus. my close-up lens has just come loose. I'm going to have to shut the camera off and get that camera back on. I believe I have that straightened out now, not sure. The 6-jaw chuck is called a bezel chuck, also called a wheel chuck, and possibly several other things, but it works like this. We have a key. This is a tool post key, this is a chuck key. We loosen that, we can drop this wheel out. Notice that the 6 jaws are all stepped in here, further out, and then they're stepped from the outside down out here. Now, this was originally called a bezel chuck because that it was used to hold the bezel of a large pocket watch to adjust to turn the groove in the bezel in order to fit the glass, an uncompressible glass, to a pocket watch. But it's found more use as a wheel chuck and the like than it ever did as a bezel chuck. If we look at this wheel, we can slip this right in to here, slip it in place, and tighten up the ring. Don't get carried away with tightening the ring. We're working on wheel teeth, but remember we're working on about 5/8 of an inch of teeth in 6 different places. 6 times 5 is 38, and that gets to being more than 4 inches of surface around that wheel that we're gripping on. Now, let's see what this situation looks like when it's running. How true did this chuck up? We touch the pivot. We touch the pivot out here and see how much tremor we have. And the tremor is essentially 0. That tremor is essentially 0. As a matter of fact, I'm surprised that it's running that true. But what we could do, we could very readily polish this pivot with a pivot polisher, work on it with a number 6 cut pivot file, things of the like. I would be a bit hesitant to really bite into this with a tool bit. And I'll tell you the reason for that. This is a Westclox wheel. This is a steel pivot that's put into a lead alloy arbor. That is not very strong. This wheel is spoked, and there is a degree of flexibility out here. I would not hesitate to work on it with any kind of polishing equipment, but I would hesitate to lay into that hardened pivot with a graver, because there's a good possibility the leverage you have that you could knock it out of the position in the chuck. If you throw it out running at high speed, you might indeed do irreparable damage. But this is what the wheel chuck or bezel chuck situation looks like. This can be worked with either the tip-over tool rest and handheld tools, or it can be worked with the slide rest that we looked at here a few moments ago. This chuck works extremely well in taking wheel blanks and turning the bore. Turn the bore, the ID, the hole in a wheel blank, because this holds and runs true. This is a very true running chuck, and you can bore the ID of the wheel blank very accurately and very readily in that. The boring tool that we looked at in Clock Chat's Clock Talk tape number 1, the little tool that holds a dental burr, is very, very fine for a boring tool for that purpose in this particular chuck. Now let's look at another feature in this. We notice as the diameter of the part becomes larger that it is spaced further and further out. That says that we can go through this stock, whatever we have, we can go completely through that down in this region and have plenty of tool run out area. A small item that could set here, you could go through by a considerable distance. The way the steps are made, it's very easy to pass all the way through with a boring bar, take up the next amount of cut, and come back out and deburr the back side of it as you pull back out with a boring bar. It's a very fine chuck, has great utility. Now, let's imagine that we're doing something else here, and let's take this escape wheel. This is an escape wheel for something of a large 60-beat clock, and I'm full of chips up in there. I'm not sure that that pinion would go all the way back in there. No, it won't. But suppose that we needed to work on this pivot out here. How could we do this? We could set this wheel right into this chuck, and I don't know whether it's proper to go to the next smaller step or pull that larger step down. Let's see what we get here. Looks like right there would be a good place, and if we're careful, we can hold that escape wheel right by that. We've got considerable run out out here on the pivot, and I wasn't really tight. Let's see what we got now. It's worse. Now, if we find that we can't accommodate that wheel in this step in this manner, we'll try one more time and see. Well, that's pretty close, but it's not good enough. It's pretty close, but not good enough. How would we polish that pivot? How could we cope with polishing that pivot? Well, probably the best thing to do is to abandon the wheel chuck completely. Probably abandon the wheel chuck and go into this with a wire chuck, something of this type. Then go into that with the wheel, and here is an exception to the case of chucking. We have many ground rules for chucking for things to be right. And one of the ground rules says that the chuck must fit the stock. The chuck must fit the stock. This one does not fit this rod very well. This is not a very good fit at this point. Now, what does that do? As we pull down and close this chuck, it says that the outer mouth of the chuck is the primary place that is holding the stock. We're holding in a small ring around. We don't hold too well. We can't hold in alignment. If the chuck is too small and we force the stock in it, it's holding it deep in its throat, and we have the same problem. In this particular case, this is a situation where that you would want the chuck to be larger than the stock you're holding. A very specific reason for doing that. Let's say that this is the chuck, and this is what we want to grip to. We want this to be larger, slightly larger, than the diameter that we're hooking up to. We want to hold it as a line contact right around here. That gives us the ability to deflect the alignment to a small degree in the tailstock. So we would set this in here, we would pull up, and we would hold just a small portion of the shank. We would pick this up. We're fairly close to being true there. Be careful, run it fast, it might throw it out. Then we go into the tailstock, and the tailstock I don't have in hand at the moment, but we pick a runner from a dead center lathe. We pick a runner that looks like this. Let's see if we can find a... I can't get that in focus there. What this runner has, the end of this is cut in a D shape. This is cut in a D shape, had a hole drilled in it initially, and then the side cut off the hole. And this makes an open-faced tailstock. We catch that. We catch this piece in the tailstock of the lathe, and then we rest on this D shape with just a trace of that pivot standing proud above the D shape, and we can dress that pivot and deflect it down into this, and it's called an open center or an open runner. And we can handle that situation, and we want this to not be too rigid so that we can flex it a little, and there is the case where that we use the larger chuck, pull down and hold just by the outer portion of the mouth. So that's a chucking technique for a special purpose. And when you hear the statement categorically that always the chuck must fit what you're doing, well, that's true if you want it to fit what you're doing. But if you want it to hold it in a line contact for a special purpose such as this, there is a reasonable and ethical reason to hold it that way. Let's shut the camera off till we find another. Let's take a look at another lathe in the Huckabee shop. We'll move in a little closer here. This lathe is a Mosley No. 2 built by C&E Marshall Company. The age of this lathe dates back into the earlier mid-1930s. It is equipped with a 3-deck tool slide and a 3-jaw chuck. The tool slide is from Hamel-Riglander Company. The chuck is a Swiss-made chuck, a little high-intensity light sitting in the midst. Note that the drive belt goes to the rear and to a counter shaft, a rather substantial counter shaft to the rear. This was made by the Ideal Tool Company of London. And from the counter shaft down to a motor, the motor being built by Howard Industries of Milford, Illinois. The motor is a 1/8 horsepower induction motor operating at 3,600 RPM, or about 3,500 RPM. The belt pulleys are that of reduction in speed, and then another reduction coming up to the headstock. By sliking a lever in the hinge joint of the counter shaft can be tipped toward the viewer, and the belt moved to the appropriate pulleys. This gives a very, very good drive system for machine work in the watchmaker's lathe. This lathe at the moment has no tailstock on it, and it is very, very, very good, very substantial lathe. The first clock that I ever built was entirely built on this lathe. That was about 25 years ago. Looking to the side, we find a couple of additional large chucks, one a 3-jaw chuck, one a 6-jaw bezel chuck, or a wheel chuck, and about 25 or 30 wire collets, a couple of step wheel chucks. We'll be doing some work on this lathe here in the next few parcels of Clock Talk, and see how these things operate. This is a view of a small section of the bench. There's a couple of lights on the bench, and immediately adjacent we find a small drill press. Let's change the focus on the camera and look at the drill press. It's about 18 inches high. It's an import from one of the countries of the Orient. This drill press costs less than $100. It has a good ball bearing spindle in it, It is good and tight. It has a 1/4 horsepower motor, and is just about idealistic for the clock shop. It serves well as a bushing press as well as for drilling and reaming. I have a pair of these drill presses, and they're identical and very, very excellent. Across the bench a little further we see the milling machine, but that is not the subject of what we'll be following here in the next parcels of discussion. Let's turn around and look at a different angle on the lathe. We're looking toward the chuck at this point, and we can see the motor, the counter shaft. This is a constant speed motor with a hand switch. Let's look at the switch on it. The switch is at this point. It is a little pull-push wire, and pushing the wire starts the motor, pulling it stops it. So with this we'll turn the camera off and we'll make a setup to do some work on this particular tool. This is the workbench clock shop of J.M. Huckabee of Austin, Texas. This is the day before Thanksgiving, 1987. Yesterday was the 39th anniversary of the marriage of my wife and I, and this has been some good years. In these 39 years we've been married, my clockmaking ability and tools has increased very dramatically. Though I did this work before we were married, it has come up through the years. Let's look in the tools that we have here and see what's in hand. This is the lathe of the previous picture. We have a 3-jaw chuck, 3-deck slide, the belt, drive belt going to the counter shaft at the rear. This drive belt, let's turn it around and look at it a bit. It's a pretty rough looking belt. It's about 1/4 of an inch wide, has a splice in it. Possibly we can see the splice here, which is a wire hook. That wire hook is made of a piece of a paper clip, and the belt itself is a piece of rawhide harness lacing material. It has been kept well oiled over a long period of time, and as such it is very, very pliable. It's about as soft as a cotton string, and it is of course much stronger. The object is to have a belt that has good frictional characteristics, that does not require being too tight, that we can carry a considerable amount of torque into the spindle of the lathe, and a vitally important situation is that it is not elastic. In my early days as a watchmaker, spring drive belts on the watchmaker's lathe was in vogue, but a spring drive belt is the most disastrous thing that you can have on a lathe that you're doing fine machine work on. Because of the elasticity of it, the drive speed is never constant, and consequently that is reflected into the precision of the cut that is being made, or the lack of precision in the cut. This lathe, the tool slide slips off very readily, and we'll lay that aside. And about to turn over the little high-intensity lamp that I use here. We take the chuck off like this, and the headstock, if need be, can be moved longitudinally on the bed. There are some occasions where this is needed, but that situation is rare. Each time that we make a new attachment to the bed, we should wipe the trash off of it and be sure that we latch down with no debris underneath the seat. This tool is locked down with the draw bolt in the T-slot, and we need to wipe it here and here and here and here each time that this is set back into position. In so doing, we always remain square when we lock down, and we can move the tool slide during the process of the work without destroying any preset squareness to the bed. The thing that we'll be doing here is let's make a screw. Let's see what type of work is required to make a screw in the lathe. We will use in the collet, use in the headstock a collet that will fit the raw material that we're going to use. The raw material here, as some of the other illustrations show, is a piece of a piece of 1/8 inch hard bronze stock. We will need to fit that to a number 32, that's a number 33, a number 32 collet, wire chuck as it's called among the watchmakers, go into the lathe, and we need to ring the piece into place and then tighten it up. Right here, I'm unable to tighten that. As I explained on some of the other lathes, the spindle characteristic is different, and collets are different in the tools that I have. This drawbar is too long to pull in this Mosley number 2 collet. The shoulder is set on this drawbar to pull in a Webster Whitcomb collet. So I use the spacer under the drawbar, and now we can pull this in tight. Just before we tighten, we need to ring the piece in place, and there we have a true running piece of stock. The block of collets that I'm using here are the collets that I consider to be my rough group. Most of these collets are in the order of 40, 50, or 60 years old. They were obtained when I was a young man, and they were used when I received them. Many people complain of lack of trueness in collets. Most of that is a function of the lack of know-how in chucking a piece of stock in them. Even a poor collet, if it will hold the stock tightly, can be made to run true. Now, let's look a little further back. Possibly we can see where the pencil is going. This is a block of tools. This is tool bits for the tool slide. Down below, the little wood dowel handles that we have here, those are handheld gravers, and if we're to make a screw, we will have to have the appropriate die. This is a bronze safety pin, if you will, that I use to store my dies on. From time to time I string them on here in die order so that I can find them, but most times I have to hunt them up. I don't have a die case. This is the tool handle that we will turn the die with, and a screw pitch gauge. We will not be using the screw pitch gauge in this particular operation, but this has little racks of screws. This particular one on top that I'm looking at right here says number 46, and looking down to the back one there is number 20. So this covers threads 20 through 46. Over in the next section here, we're covering much coarser threads. We can see that is a very coarse thread there. As a matter of fact, it's the pitch is 4 per inch. This is a machinist screw pitch gauge rather than a watchmaker's gauge. But if we're attempting to match a thread and making a nut or making a screw, we place this gauge in mesh with the screw, and we find the thread that perfectly fits, and then we read the pitch on that. That is a must tool if you do any serious thread cutting. This is a tap handle. It's not very big. That's about 4 inches long. It's one of the smaller tap handles. Actually, most taps down in the size that we're talking about should be turned with a pin vise or between the fingers. The smaller taps should be turned purely between the thumb and the 4 fingers. This tool here is a pretty famous tap breaker, particularly for the smaller ones. Making the tool, we need making the screw. We need measurement device. We work many workmen work to a pattern or to a fit or whatnot. Due to my machinist background, I always work to a dimension, work to a predetermined dimension. A stick rule, which we will be using. This is one that we discussed in an earlier picture, and of course a pair of tweezers and the eyeglasses to keep the chips out of my eyes. This pair of eyeglasses, this is a pair of commercial safety glasses with tempered lens. Very good, very high quality safety glasses. In the left eye, right up here in the corner, I have an eye loop that compares to a kind of a median range loop that would be used by a watchmaker. This is trifocal lens, and the frames are unbreakable, and the glass is very durable. I wear these at all times when I'm running the machine. I do it for 2 purposes. One is to see, and the other is to protect the eyes that I have no replacements for. Now let's talk about a screw. Let's make a screw from this stock, and let's make this screw in a tiny size so that it's easy to make. Generally speaking, in machine work, you'll find that smaller is easier. Smaller is easier. And that is true until you get down extremely tiny. The reason for that, there is less metal to remove, it's easier to handle, as long as it can be readily seen and is within the range of working tools, then smaller is easier. I will make the screw from this 1/8 stock, and we'll make the head something that is commonly called a cheese head by the Englishman, or possibly a pan head, or the type of head that we generally see on in the older clocks. That is a head that is purely a cylindrical prism, a short cylindrical prism with squared edges around the top of it, and not square right angle edges on the top of it, and a slot in it. And we'll make the diameter of it approximately the 1/8 of an inch. That is the diameter of the head. And in doing that, the appropriate thread is the thread of a number 1 screw. Now, if you may not be familiar with screw numbers, we have this system that is called the machine screw thread system. Not machine screw. I'm sorry, not screw machine. Screw machine is a type of a tool that makes screws. Machine screw is the proper designation for the particular screw. In that system, what is called a number 0 screw, or more commonly called an aught size screw. The aught size screw, the OD of the threads is 60 thousandths of an inch. That is an aught size. If you will listen carefully and remember this key to memory, you can always carry the dimensions of machine screw threads in your mind. A number 1 screw is larger by 13 thousandths of an inch. the aught screw is the base number of 60 thousandths of an inch. The aught screw is 60 thousandths. On number 1, you add 13 thousandths, or it is 63 thousandths of an inch in diameter. A number 1 screw takes an additional 13 thousandths, or 26 thousandths, added on to 60, so that brings you to 83 thousandths. I'm sorry, to 86 thousandths. 86 thousandths. Twice 13 is 26. Added to the 60 brings us to 86. When we get to a number 5 screw, it is 5 times 13 plus 60, and that brings us to 125 thousandths. Or a number 6 screw is 13 additional thousandths, or 138. And these numbers go all the way up through, I'm not sure how high, but through number 12 is commonly used today. I understand in the distant past that they went on up into the 20s or even higher, but I never see a screw larger than a number 12 in machine screw threads today. So we will be cutting the tang of this screw, the tang being the portion that will be threaded. We will be cutting that 60 thousandths plus 2 times 13, or 86 thousandths of an inch in diameter. A tang of that size will give you a 100% thread. 100% thread brings the crest of the thread to a sharp point. It's not prudent to make 100% thread unless you really have a reason to. The reason being, it is very difficult to pull 100% thread through a die. I usually size my screw tang 1 or 2 or 3 or 4 thousandths of an inch smaller than the 100% thread. I like to approach the 100% thread because that when we tap the holes for it, I like to make the thread about an 80% thread to guard against damage of the tap. So we'll be turning a tang on the end of this stock that is 86 thousandths of an inch in diameter. We'll make this some arbitrary length long, probably in the order of 1/4 of an inch. We'll make the head 1/8 of an inch in diameter, and we'll cut this off, square up the head, and then the only thing that will remain is to saw the slot. I usually saw the slot on a little milling machine that I have, but it's perfectly acceptable to saw the slot with a jeweler's saw, and you may need to touch it up a little bit with a screw head file to dress up its appearance a bit. Let me cut the camera, and I'll make a few tools set up here, and then we'll proceed and we'll make the screw. We've turned the camera on again, and while this camera was off, I discovered a problem for which I don't really have an answer. Let's look at this tool holder. This tool holder is a slip-in holder, and there is an eccentric washer underneath this that is not in round but in flat. I'm not sure that's the proper term for it. This washer is thicker on one edge than it is on the other, and we can rotate that washer and raise and lower the tool bit. The problem that I identified is the fact that I am not going to be able to get the camera on the work because of the shadow of the tool holder. And what I'll do is part of the work with the tool slide, and then I will do the remainder of it with a handheld graver so that possibly we can see this better. We set the tool bit up approximately on center, tighten it with the key, and the first thing that we will do is square the end of the stock that we have in the headstock. We'll square that off in order to use it as a point of measurement. We have the dial gauge for the longitudinal feed. I do not have the dial gauge in for the horizontal feed. This will mean that we will get that dimension empirically going across the lathe. We can measure it going longitudinally with the lathe. I will square this off on the end, make a cut 1/4 of an inch long, and take the dimension to the diameter of a number 2 screw. I'm sorry, of a number 1 screw. Remember that the number 1 screw is 60 plus 13 plus 13. These are in thousandths of an inch, or that is 86 thousandths of an inch, and I want to run a little short, just a little short of a full thread. So let's say about 80 to 86 thousandths of an inch that we will look for. Let's start the lathe. I don't believe that we've had the lathe running at all in this set of pictures. I need to lower the tool bit slightly. I'm above center. This looks about correct, and we'll start the lathe. The motor is pretty noisy. You can see there's a little whip in the belt. If you're doing fine machining, if you're doing the finest machining, the highest precision, you cannot tolerate that belt whip. That must be suppressed, because it gives a tremor, a slight tremor to the lathe. The usual way of doing this is to adjust the speed, change the speed, or change the belt tension, or have something to touch the belt to reduce the whip. You may have noticed when we were on tape number 2, the little lathe without the counter shaft on the rear, the belt whip was pretty bad on it at that particular time. To get down to finer, higher grade of machining, we would need to adjust that belt tension to take care of that. Let's have to move this over a little, have a conflict with the headstock. Still have a conflict. Where is it? Okay, I've run out of range. I've run out of range in my dial gauge, in the spindle travel of the dial gauge. Now, the thing that I will need to do is back out a considerable amount, come down here, back out, lock up the, lock up the cross slide. Now I need to extend my tool bit in. We'll do this with the slide number 3, that is the top one. We'll bring that in so that we can reach the material that we're on, and we'll move the tool post holder down a little closer to the spindle. Now that should set us in order. Let's try cutting the first cut, which is to square the end of the stock. I still have a problem here. Let's try that. Okay. Go across, and I find the tool bit is yet above center, leaving a pip in the middle. The tool bit is scrubbing. I'm too high. The rake is too small an angle for the height of the bit. Move it down some. Look again. All right, we're cutting good, clean chips, and let's do this. I'm going to go in and touch down ever so slightly on this stock, right at the point of the squareness at the end of the stock. Now we'll turn the gauge. We'll turn the gauge to 0. My gauge is set on 0 at this point. Cut this tang 1/4 of an inch long. Reduce the noise a little. To cut this tang 1/4 of an inch long, I will need to make 2 1/2 revolutions of this gauge. I will need to go 2.5 revolutions. Let's see what that looks like without the machine running. There's 1 revolution. That's the first 100,000ths of an inch, the second 100,000ths, and I've run into a problem here again. I've touched down bottom on this, so we'll have to gain a little space in between here with our setup. Let's do that by moving the tool post over some more, and we'll see how that is. Let me touch down. There's a touchdown. So at the touchdown being I have moved the tool, I have to have a new 0 point on the dial gauge. All right, there we are. We back out so the tool can pass by. Here's the first 100,000ths, second 100,000ths, and 50. So we'll need to dial in to that point to get the tang of the screw 1/4 of an inch long. That gives us measurements in thousandths of an inch. Let's try again. One, two, and we'll leave a little to finish up on and about 7 thousandths short. We back out and make another cut, and we're continuing to cut. Let's see if we can see what the cutting looks like. Let's see if we can get this. This is one of the spiral shavings that was coming off of the stock while we were cutting there. All right, let's measure the tang diameter and see what we have. I need to look, and what I see appears to be correct. What I thought I was seeing. I had rotated this top slide in some of the previous illustrations, and I look at the tang that I'm cutting. It appears to have a slight taper in it. I'm off of 0 on my azimuth adjustment. All right, that sets us back and should take care of that. And we look at the measurement. If we measure this way, we lift the instrument off and look like this. I'm measuring 92 thousandths of an inch, which is not too far from where we want to go. If I measure this way, I can lift the instrument off and look like that. I'm measuring 92 thousandths of an inch. Now we want to take this to somewhere in the order of 80 to 86 thousandths. See what we have now. I removed about 2 thousandths of an inch. The cut looked fairly large. The cut appeared to the eye to be larger than the 2 thousandths of an inch that I removed. So we ask the question, why the mistake in judgment? There is seems to be a mistake in judgment. The situation was this. The tool slide was turned this way. It was off 0 in this direction. That means that the end of this piece that I was turning had the ice cream cone shape with the mouth pointing that way. And I was measuring the diameter against the end of the cut, which was a smaller section. So naturally, as I was trimming the larger portion in the first part of the cut, the shavings, the swarf looked larger than I had expected. Let's continue. Let's look at some of the shavings that's coming off of this. Again, we're pulling off a the cuttings looks like this. See if we can find that in a focal point of the camera where it can be seen a little better. These are about better part of an inch long. If we look at this, let's see if we stretch this out. Can we find a place that we can see the shaving that's coming off? All right, how about the measurement? The measurement is right on 80 thousandths of an inch. Now, think again the diameter we're looking for. We're looking for 60 thousandths of an inch for an aught, 73 thousandths of an inch for 60 thousandths for an aught size, 73 thousandths for a number 1 size, and I believe when I said that number 2, twice this, that I made a mistake up early in the dimension. When I look at this, I see the tang is larger than I recognize for a number 1 screw. Let's go back and think again. 60 thousandths for the aught, 60 plus 13 for the number 1. 60 plus 13 plus 13, as I mentioned previously, would be for a number 2 screw. So I need to go down more. I need to go down to the 73 thousandths of an inch, and that should be trimmed a little less than that, so it should be in the order of about 70 thousandths of an inch. Let's go down a little further. I am pretty remarkably here. I have to get where I can see this in the light. Unbelievably, I'm on 72 thousandths of an inch there. Let me measure again and see what the taper might look like. I have ever so slight taper on that, about 1 or 2 thousandths of an inch taper in that distance. Let's go back now and end the screw at 1/4 of an inch long. Let's say for some reason that we want this to be exactly 1/4 of an inch long. I had readjusted my tool bit, so it means I have to readjust the dial here again and go in 1/4 of an inch. Here's 100 thousandths, 200 thousandths, 250 thousandths, and have just a tiny cut that needs to be made to come to that value. Now let's go to another mode of operation. We'll take off the slide rest. Isn't it wonderful how that tool will slip off and go right back to the handheld tool like this? That's really, really quick change operation. The thing I want to do at this point is to chamfer this edge, this leading edge, which allows me to enter the die easily. There's a problem in entering the die with a square end, so we want to chamfer that. We'll do that with a handheld graver, and let's see if I can get my hand down. I don't know if we can get that where it can be seen or not. Possibly you can see the chips. I think possibly you can. Now the second thing that we want to do with this handheld graver, I was turning with the tool slide rest with a tool that is a round nose bit, slightly rounded nosed bit. I want to go back and square up the corner, square up the shoulder of this screw. which is the under part of the head. Obviously, we don't want a radius of significant amount underneath the head. So let's square that up. Get down here and look closely to be sure that I have this square. The light level is not too good. There is a particular problem here. It is very easy to overdo the light level with this camera. This particular camera can almost see in the dark, and light levels that are good to work with are almost too bright of the camera. All right, we've squared up the corner. Now, we'll remove the tool rest, and let's bring this out a little further so that we can look. Well, in the monitor, I don't think I can see that. Let's bring it out this way. Maybe we can. Still can't see that. We need some non-reflective background. I just can't seem to find a spot here that this is really visible where we're sitting, but believe me, the tang is there. I have a little burr. I have just a little burr on the shoulder, which I want to remove before we proceed any further. Back in the lathe with the handheld tool, and we turn this on. I'll touch that burr right on the corner. Okay, that does that up nicely. Here is a piece of material that you may or may not recognize. This is something 3M company makes. It comes in a sheet about 4 by 6 inches for about $1, I believe, and it looks kind of like steel wool, but it's made out of plastic. It's made from plastic, and embedded in that plastic is some type of 3M proprietary abrasive. That is a great polisher of the fresh made parts. This brings this to a nice finish, takes off the blemishes, the scratches, and whatnot. Now, next thing we'll do is thread that tang with the #1 thread. I'll turn. Let's see what's in the die. That has an 832 die in the holder. I'll turn the camera off. I'll locate the appropriate die here, put it in the die stock, and turn back on, and we'll continue. Turn the camera back on, and I regret that I didn't search for the die while we were on camera. This particular die here is 832, and the trademark on it is NC. I have no idea what. No, that's not the trademark. That's National Coarse Thread. I don't even know that there's a trademark on that one. This particular die here is brown and sharp, looking a little further. This die here is GTD, and I have no idea who that is. This one is GTD. This one is Union Card. GTD. That's a Hanson. This is Vernon, and so on. What it amounts to, these dies have been obtained over the years. They're cats and dogs, but they're all good dies, and every one of them gets used on a pretty regular basis. Let's look at a larger one here, and we'll see some characteristics of the die. This die is split, and it's split right in this area, right in the edge. See if we can find a place that we can see this. Possibly there. We're split there, and then there's a jack screw in the edge here. So you can increase or decrease. This die is as a C. We can increase or decrease it to make it cut a slightly larger or slightly smaller thread. This is a number 12. This is a national course. It's number 1224 thread. Now, when we place this in the die stock, it's necessary that we pull the screws in the die stock in tightly, because that die will stretch in the slack in the stock if we do not do that. Never, never, ever attempt to thread without this being in a die stock, because it will stretch and it will break in the backbone. If you attempt to use it without being in the die stock, it is sure to break. All right? Let's see the problem in doing this. We look at the die. We find this is the starting side on it. Usually the label will be on the starting side. This says National Fine 1-72. That's size 1, 72 threads per inch, made by Union Card Company. The die stock, this says OK number 751. This die stock, this particular die stock, was a piece of World War II surplus. I've had it around a long time. We place this on the tang that we have and square it up best as we may by eye, and we turn the lathe by hand. Pure and simple. And I get down here and pull the belt like this when things starts going good. I turn this until I hit bottom. Back out. I'm going to show you a little trick that's technically not pure, but works to a degree. We find that there is a run out on the thread right up against the shoulder, and we would like for that thread to go right to the shoulder if at all possible. We turn the die bottom up, which says that we're putting it on backwards, and the die doesn't cut good in that direction, but there's only a small amount of thread that needs to be touched up back at that point. So if we pull on, and some reason I'm slipping in the collet, that's what the situation is. I'm tight there, and that will carry the thread a little bit closer to the head. If this particular screw must be used where that it's screwed down against nut or base plate or whatever it might be, and that presents a problem, you would say, well, it needs a washer under it. Well, that's really not the solution. If that screw has to meet that particular type of application, then the thing to do is to take the handheld graver and go in here and undercut a little bit in that area. Undercut just ever so slightly in that area. That takes out the imperfect thread in about the last half turn. That solves that problem. When you make the screw, you look at that. We'll take this 3M abrasive, put it on the, it's not very abrasive, it's more of a polishing cloth. Put it on the threads and back that out. Now, we have the screw at this point finished in the tang, and we go to the next operation in which we'll saw it off. We'll saw this off with about, I have the blade in my saw backwards. I boasted around here on one of the previous tapes that you just rub your finger over it and you always have it right. It looks like I didn't rub my finger over it or didn't pay attention to what I was doing. All right, we'll saw this off. I usually ride my finger under the frame here to catch this in case the blade should break or in case that it should fall off, the piece fall off. I hope we don't lose this when it goes off, as we did in some of the things yesterday, in the previous tape. Actually, the previous tape was made yesterday. If you saw against your finger here, and the question is, am I going to saw my finger off? Well, I don't think so, because if it starts cutting my finger, I'm going to quit pulling on the saw handle. I'm sawing very lightly here. I want to get essentially through. There it is, and we have it in our hand. Now, we're looking at a screw that's approaching being finished. Try and get back into the... Let me see if I can touch this focus a little bit here. We're zooming the lens to try to find a place that the focus will be a little better, and really not doing too good. What we'll have to do when we get this finished, we'll put on a close-up lens and look at this screw with a critical eye. Alright, this is the screw. It's a 1/4 inch long. It's a number 1. We need to finish the head. There's a burr on the back side of the head. So let's see how we handle that. Take out the collet. We look in our collet block for one that this screw will fit, and I think that it's number 17. Let's see if I can... Looks like my number 17 is out of the... Here's the number 17 right here. Thought the 17 was out of the block. This just slips into the number 17. This is a case where we want the screw to fit the collet perfectly, because we're holding down against the threads, and we don't want to damage those threads. But the number of threads that we have in the area that we're holding, and if we take a light cut here, we won't have any problem at all. Put that in the lathe, and ordinarily, if I were making screws, I would cut that with the tool slide rest. But in this, let's just do this with a handheld tool. Set that up there. Let's find a tool that feels quite sharp. Go in here and trim up the head. That tool's not as sharp as I thought it was. Matter of fact, it's pretty dull. It needs to be sharp. Oh, now we're fine. And we're looking at this. I'm going to move the light in just a mite so that I can see. And I'm going to start catch a center in the head of that screw. Catch a small center in the head of the screw. What is the purpose of the center in the head of the screw? Well, pure and simple. When we go to saw the slot in it, we'd like to know where the exact center of that screw head is. And just a tiny center gives us the marker that when we go to saw the slot, that we'll be able to locate that center. All right, let's move out here and touch this with our polisher just for a mite, and let's inspect to see whether or not we have gone into any damage on the thread. I might take a look here. I don't readily see it, but we can determine that by running this screw back into the die. A good sharp die will cut the threads perfect enough that we can go back into the to the die approximately with finger pressure. So we've had the screw back in the die, and we take it out. Now, the only remaining thing to finish, totally complete this screw, is to saw the head slot. Now, I'll turn this camera off, and I'll see if I can get a close-up lens on this, that we can get this down onto something that we can look at it and inspect it as far as its quality and appearance is concerned. We're back on the camera, and I'm not having too much success in looking at this screw. Let's try turning it a couple of directions here. I have the camera lens less than an inch from the screw, and the lighting is such that the reflections don't permit too much view of it. But remember this, the screw that we have just made has a 1/4 inch of threaded length, and the thread pitch is 72 per inch, and the diameter of that screw we discussed early, it is about 72 or 73 thousandths of an inch in diameter. So the screw that we're looking at on the TV screen is many times full size, but this is a screw made of hard bronze, which is as strong as commercial steel screws. It will hold a finish for a long time, and it can be nicely polished. We have yet to cut the slot in the screw head, and we'll look at that a little later. Let's look at the screw situation now. Here is the screw that we have just made, and compared to the size of a number 2 wood pencil, you can see that the length of the screw is approximately the total length is approximately the diameter of the pencil. Now, the question is, how do we handle sewing the slot in it? Here's the little vise that we looked at in a previous film. It has a V notch in the jaw, and we very gently pull up on that screw in that V notch. That holds the head in a good firm position down close to the jaws of the vise, and at that point we will take our saw, and I'm sorry the saw is on the other side of the camera. We'll take the saw and start right across the head at the marker that we turned at the center mark, hold that against our fingernail, and saw until we carry it the depth that we would like to have the screw. Once that slot is cut, and we may need to widen it slightly with a screw head file, then we take the screw, go back to the lathe, and deburr it. We can deburr that with a fine cut file or a stone or what have you, and you have the perfect screw. The question that may arise, why do we make the screw? Well, in the first place, if we had a screw, we wouldn't be making a screw. That's the primary answer to the question. And if we are building something that needs a special screw, it's simple enough to get the correct length, correct diameter, correct thread, or what have you. Screws are really not all that difficult to make, and you may ask, well, how long does it take? I built a couple of clocks last winter, and I had, I believe it was 16 screws in the clocks that was this size. There was a total of about I think about 18 screws in each one of the clocks, but I think there was 16 that was approximately this size. This is an easy size to make, and I timed those. What I really did is go into the lathe, make a setup, make the cut, take the stock out of the lathe, put another in so that I didn't lose time on the setup. I wound up with a total working time of a little over 5 minutes per screw to make these. That's a pretty expensive screw when we're talking about labor charges per hour, but you have, if you can make the screw in 5 or 10 minutes and you have it in your hand, that compared to laying up the job, placing a special order, paying the transportation cost, get back into the job again. There is certainly times that the decision to make a screw is the right decision. And not universally, but there is a time for that. Larger screws, and right now I seem to regret that I didn't make a larger screw for this discussion, because it would have been much easier to see the end result. Usually when I'm making screws, as when I make clock bushings, while I have the setup, I usually make some extras. In this container here, I have the overrun for a number of screws that have been made for special purposes. Let's take a look and see what they look like. This looks approximately like the screw that we made in size, except it is shorter in length. Several of these look about that way. I notice one or two of these has a rather sharp point on it. Apparently those points were made like a 60-degree included angle point. Apparently they were made for some specific purpose. All of these are handmade. This is a number 5 screw. I wish I could get the image of the head on it. The dimensions on a number 5 screw, as this is made, this would be what the Englishmen call a cheesehead screw, each of these. The dimensions that I commonly use for the number 5 is a 1/4 inch diameter on the head. Make this about 3/16, make the head about 3/16 inch deep, unless there is some other reason that would change that. The threaded tang on a number 5 is 125 thousandths of an inch in diameter, and the classic thread for a number 5 screw is 40 per inch. Here are some small nuts. I don't know what that nut is for. It appears that that's a nut one size larger than the screws that we have here. Now, if we look around, let's see if we can find the screw that we made here this morning. It has to have no head on it, and I can find it right here. You probably can't see that in the illustration. You say, how did I find it? Well, it's a little bit brighter than the others. We polished off that head when we made it, and I spotted that, not because of the lack of the slot yet to be cut in it. I spotted it because that it was a little bit brighter.